Good morning, everyone. Today, we will continue to study the singular numerical relativity. We know that the singular numerical relativity is the completion of general relativity. We need to complete relativity for one reason. The reason is that relativity did not fulfill yet its own mission, the responsibility attributed to relativity. It's about measuring events in space and in time. By definition, relativity is the field of study that measures events, things that happen, where and when they happen, and by how much two events are separated in space and in time. The definition is very clear that we need to measure events, identify them in time and in space. But so far, we have not been able to do that. That's why we need the singular numerical relativity. The singular numerical relativity will help us to quantify space-time. By quantifying space-time, we will be able to resolve all the little issues of quantum mechanics centering on the measurement of space-time in quantum mechanics. So we will solve the problem of measurement in quantum mechanics, and all the other problems will be solved. Because in quantum mechanics, for example, we say that particles can be in many places at the same time. We need to know how many locations that particles can occupy in space-time, and how much each location can contain. So we need truly to tell how many locations and how much per location. And to do so, we need to measure space-time. Speaking of measuring events, we know that events can happen in different places at the same time, in same place at the same time, in the same place at different times. So events happen that way because life is made of events. Without events, there is no life. Our existence will have no meaning at all. So what we have to understand by event here is that anything that happens, even moving my hand here, we don't need to be too much into quantum mechanics viewpoint of events. But events are general. All happen in the universe are events. So as you see, events can happen in different places. But Einstein came up with a very radical idea regarding the events that happen in different places. For him, he says, yes, it is likely that if the events are generated by the same source, this event will be simultaneous. Likely. But it is not absolute, because all depends on the state of motion of the observer. So Einstein insists on the state of motion of the observer. So events may be simultaneous, but there is a condition. What is the state motion of the observer? So let's see, for example, this woman here sitting at home eating some cookies. For her, if two events will happen, even these events are generated by the same source, for her, there are two possibilities. If the events are making noise, for her, she may hear them as bang. It means they happen at the same time. And it is also possible that she will hear them as bang, bang. It means different times. But for this guy here who is riding his or is driving his sports car, Einstein says, no matter what, the two events will be absolutely separate in space and in time, because this guy is moving. So let's forget a little bit about the notion of speed of light, because actually the idea of Einstein was to just tell us that when motion is implicated, then they must be space and time. Motion implicates space and time. For someone who is moving, absolutely, there will be different times for the two events. They will never be simultaneous, meaning they will never have the same time. Then the reason is that space and time are entangled. When we say that space and time are entangled, you may not truly understand it, but I know that it is very easy to understand, in a sense that when the event A happen and event B happen also, they have each one its own space and its own time. Then, therefore, there is a separation in space and a separation in time. That's what we call in space spatial and in time temporal separations. Then Einstein said that the time between the two events will depend on how far away they are located. So the distance between the events will determine also the time. Why? Because time and space, as I explained already, they have one thing in common, and which is length. So you move from a point to another point in space and in time. It means the time we are talking about here is not like 10 o'clock. No. The time we are talking about here is like 1 second. And the second means tick tock. You have a initial point and an ending point, the final point. The same for space. Therefore, if you move from a point to another, you are carrying space and time with you. Therefore, you form a bit of space-time. So you have a bit of space-time. And that bit of space-time can be written like this. So anytime you will see we write it this way, or this way, or simply we can write it as a space-time interval between 2 points. Therefore, we can calculate exactly the distance between the 2 points, the distance between the two events. And Einstein, with the help of his professor Minkowski, they came up with this formula, which says that space-time interval equals the space interval here squared minus the speed of light multiplied by time interval squared. This formula is good, but just for objects that move at the speed of light. And we have to understand that the thought experiment of Einstein that led to this formulation was based on the speed of light. Therefore, we can't blame anyone for this. It is good as it is, as long as the speed of light is concerned. But we have to know one thing, that not all the bodies of the universe that move at the speed. My God. Not all the bodies of the universe move at the speed of light. We know that the majority of bodies, 99.9%, they have mass and they don't move at the speed of light. For this reason, we really need to refer to the only law that was discovered where the standard motion works. It means we have to refer to Galileo, because Galileo measured the speed of objects in free fall, and he came to the realization that all objects fall at the same rate. So what do we mean here? That we need a condition of speed which is adapted to all objects, and that is fulfilling what we call the equivalence principle. You understand my point? So we need only a condition where all bodies can be involved, because we are not going to deal just with light. In the universe we have so many bodies that do not travel at the speed of light. Therefore we need at least here where we have the standard motion for all bodies of the universe. And here Galileo measured the speed of objects in the free fall. He found out that the distance an object travels is directly proportional to the square of time. Distance equal time squared. Here, as you see, if you go from 0 to 1, this is the first unit of time and distance. Then when you move to the second point in time, the object will travel 4 times. It means 4 equal 2 squared. 3 squared, 9. 4 squared, 16. So you can continue. And here it means all objects in the free fall obey the square law. So here we have to relate the standard motion with the square law. The standard motion is what we call the free fall. And that's what Galileo measured. Therefore, for us to measure the distance or the space between different points, we will use this as the ruler for measurement of space-time. That's why we call it Galileo's line, Galileo's ruler of space-time. The Galileo's line of space-time is coming up. So here, as you see, distance equal time squared. In our conventional physics, we know clearly that distance is calculated as speed times time. So velocity times time. Therefore, in order for us to understand exactly what this d equal t squared means, we have to refer to this conventional formula that we have. And it suggests here that when an object is in a free fall, the speed will be equal to time. V equals t. So it means one of the t's here is representing the speed in the formula. And to see exactly how it works, let's see it through this the graph here. We have a graph This is the axis of x, which is space, and this is time. We say that when an object is in a free fall, the speed is equal to time. First of all, what does it mean? I already explained last time that for us to understand exactly this formula, we need to understand that what Galileo measured here were only the units. So the results you get in calculating all of these are only the units, and they give us very clean formulation which is dictated by numbers. So the numbers which come here, so you have point 0, you can mark here 1, 2, 3, 4, 5, etc. 1, 2, 3, 4, 5 in time, same. So you do that, but at every time when when the object is in the free fall, at every point on this line, the object speed equal to the time as the number of units. So if my time here is 2, therefore the number of units of speed should be also 2. Then when we mark all the points, we go, for example, here with this is point A, time and speed. B, time and speed. They meet here and they meet as squared. So because we are dealing with time squared, so the value we get here is a squared number, here squared number. So we can continue making all of that happen, and we will have a line that goes on 45 degrees. We call Galileo's line of space-time. So on Galileo's line of space-time, all the values are squared values. So we'll have only A squared, B squared, C squared, D squared. You can continue, etc. You can continue. So you will have all the values that you meet here are squared numbers. Why? Because speed equal time. It's very simple to understand. Now, because this all the values that appear here are squared values, then if you go from a point A to a point B, then you will go from this point in space-time, from this point here to the point B here, and you describe an area, a two-dimensional area we call the square arrow. And the square arrow, as we learned already through the numbers, the singular numerical relativity, the square arrow is the difference between two squared numbers. So if you are moving on the line of space-time, because all the numbers are squared numbers, so you are moving from a squared number to another squared number. This squared number can be closer or far away, it doesn't matter. But what you are describing will be an area. Anyway, we will, so it means this line here, the distance we have here, we call the square arrow, is equivalent to the area, which is a two-dimensional area. And you will understand soon why it is so. Therefore, you go from point A to point B. For you to calculate the distance here, which is exactly the square arrow, you have to get b squared minus a squared. Now, what is the difference between space and space-time? In our conventional geometry, it means the geometry that we use in schools, we use at work, we use everywhere. In this conventional geometry, distance is the separation between 2 points. So you go from a point to another point, and that's only one dimension. Area is 2 dimensions, and volume is 3 dimensions. All of these are 3 aspects of space. So in our geometry we use, these are considered as space. 1-dimensional, 2-dimensional, or 3-dimensional. But in the geometry of space-time, we have motion. The geometry of space-time is applied to only moving objects, moving bodies. It means here we are moving from a point to another point. Therefore, time is implicated. Motion implicates time. And for that reason, distance becomes 2-dimensional. So you are carrying a dimension of space and a dimension of time. Area becomes 3-dimensional, sorry. Then volume 4-dimensional. All we call this space-time. But as we know, I said from the beginning in my introduction to these lectures, I said from the beginning that we are going to study space-time in just 2 dimensions only. 1 dimension space and 1 dimension time. Because that's how we can understand how gravity works at the foundation level or at the fundamental level. So here it says that when you move from a point to another point, as I have shown in the diagram above, we saw that you move from a square point to another square point, then that gap or space between them is called distance, and that's what we call the bit of space-time. So distance means bit of space-time in the geometry of space-time. Space means the average speed that you will need in order to navigate from point A to point B. That's what we call the space. So this is a new understanding that we are introducing here about space. Speed is the unit of space-time. As a matter of fact, we use meter per second, mile per hour in order to express speed. So that's how we express speed. It means there is space, then time. Space, time. That's why speed is unit of space, time. These are things that you have to truly understand. You don't need to speculate regarding this matter. For with all of this understanding, now we can measure the bit of space-time. Measuring a bit of space-time, we go from point A to point B. We call it starting point and ending point. In time, it will be the initial time and the final time. On the line of space-time, so you must imagine that you are directly on the line of space-time. Everything I'm going to say here is about the line of space-time. So do not understand it differently. Because on the line of space-time, we move from a point A to a point B. Each point here represents time as A and B simply, then distance as A squared and B squared. So the value of each point on this line is double, in the sense that it indicates time and space. But what we will be given only is always time. If you know time, then you square. For example, here you have to square you have to square A, and here you have to square the B. So if you move from a point A to point B, describing this bit of space-time, the bit AB, then the total space-time between the 2 points is calculated as B squared minus A squared. You see that there is a resemblance with Minkowski's formula, with the minus here and the square here. We saw that in Minkowski. We saw that. Then, when we do the transformation of this formula, you notice that this is in algebra what we call a remarkable product. And it is transformed as B plus A multiplied by B minus A. That's what we call the distance between the 2 points. So you have, then what do they represent? As we have seen already, this represents the space-time interval. So you move from this point to a point. That's why we talked about the interval. So the space-time, or the bit of the bit AB, the bit of space-time between the 2 points here is called, or the distance is called the space-time interval. You write it this way. Then, according to the formulation, we know that distance equal speed times time. Now, where is speed? Where is time among the two here? Because we are going to multiply speed by time. Of course, on this line, as I have said already, you move from the initial time to the final time. Therefore, the time is the difference between the two, which is final time minus initial time. So you have B minus A. So B minus A represents the time interval or the time elapsed, meaning the time you need in order for you to travel from point A to point B. This is the time elapsed or time interval. We write it this way. Then, conclusively, we can say that what is remaining here should be the speed, because we know now the time B minus A. So the B plus A should be the speed. This should be the average speed. Why we are talking about average speed? Because in the free fall, the speed of the object is changing all the times. Therefore, you cannot speak of constant speed or instantaneous speed. There is no such a thing. What you have to know only is about the average speed for you to travel a certain distance. So the average speed is what we call the space interval. This is where I'm coming back to what we said already when we saw the difference between space and space-time. That in space-time, space means speed. Means speed, velocity. Okay? This is a very brand new idea that you have to just absorb. You have to understand that way, because you cannot get it better than that. So now let's see how we can really calculate these things based on the time interval, because this is the time we travel here. Then we know that only the time is given. Therefore, we go from the initial time to the final time. And we have seen that through this formula, we see that the space-time interval equal space interval times time interval. Then time interval is the final time minus the initial time. Then space interval is the final time plus the initial time. This is a very surprising thing. It's something that I struggled a lot with, because how come that you get to know the speed, you have to get just this number plus that number? It's I could not believe, but that's the way it is. You may have also the same problem. How come that the value you have here and here give you directly the average speed? That's the law. It's not me who is making that. So now we have to replace the final time here by its true value, which is initial time plus time interval, because we want to convert everything to time interval. That will be our base. Then when we do that, we replace this value here, then it gives us time initial time plus time interval plus initial time. So you have 2 times initial time plus time interval. So you can use this formula or use this one. It is the same. You get the same results, but you have to have all these considerations done because you have to broaden your knowledge regarding this. Then in the situation where we have now 2 consecutive points, it means you move on the Galileo's line of space-time. You are moving through different values. You go from A to point B, but this time we consider that you make only one step, and here we are using A and B, but in the Galileo's line there are only numbers. So there is precision. We don't need to speculate. It means you are moving from n number is your starting point for event A, and n plus 1. In the same token, we say you move from t, which is a time, initial time, to initial time plus 1. Consecutive means which follow each other. So it means you make only one step. You make only one step. That's what consecutive means here. Therefore, you are moving from n squared to n plus 1 squared to ti squared to ti plus 1 squared. And for you to get this, if you transform this, you calculate this, you have this value which is 2 times time interval, 2 times time, initial time plus 1. So the 2 times initial time plus 1 is your square arrow. It means the value that you need in order to go from the square value here, which is time, the initial time squared, to initial times plus 1 squared. So this is the difference between the two. We call the square value. Then we can now show you exactly the values we get here. So when you are calculating the interval, space-time interval, you have to calculate first the time interval, which is 1, as we said, because we are moving from n to n plus 1, so you add only 1 in time. And you have to calculate also the space interval. The space interval is equal to 2 times time, 2 times initial time plus 1. And if you multiply the two here, time interval and space interval, they give you exactly this value. 2 times time interval plus 1. That's the space-time interval between the 2 points. Now let me give you a concrete example where we can see this clearly. You move from a point A to a point B, and here we give directly the values. I told you that in actual there is no such thing like A, B, no. We have real numbers. So we have 3 and 4. If you are moving from 3 to 4, your time interval is 4 minus 3 equal 1. Then your space interval is 2 times initial time, which is 3, plus time interval, which is 1. Therefore, you have here 6 plus 1 equals 7. We can see exactly now how to calculate the space-time interval. Of course, we said that we have only to multiply because space and time are entangled. So space and time are like north and east. So they cross each other. It means you have to multiply. So you get this value here. This is the 1 multiplied by this value in the interval here, and you have 7 times 1 equal 7. The 7, I put a sign here. This is only a sign which indicates that this value is not an ordinary 7, because when you are traveling from a point A to a point B, you are carrying the line of space and time. So here there are 2 dimensions that are hidden in this portion. That's why we have a 2-dimensional result. So the result which happen here is 2-dimensional. I will explain it very soon clearly so you can understand. But now let's move, and we can still do it another way for the calculation. If you are given this bit, the bit 3, 4, then you know that this is a squared number, this is also a squared value. Therefore you have 4 squared minus. So this is the shortest way you can calculate the space-time interval. You just get the b squared minus a squared. See, 4 squared minus 3 squared. That gives you 16 minus 9 equal 7. And that 7, as I have just said, is not an ordinary 7. That 7 is a 2-dimensional 7. And then you follow again the transformation. If we go to algebra, as I said, as a remarkable product, you see that the space-time interval equals 4 plus 3 multiplied by 4 minus 3. Then it gives you 7. I will explain why we need to do all of this, because you may feel boring, but why repeating almost the same thing? No, I'm not repeating things. All these are very important for you in the future when you will be doing your calculations. So let's move to the second case. Is a case when we have 2 alternate points. You move from point A to point B. This time the point A is 3, and you are moving to point 7. As you see, you have values between 3 and 7. The values are 4, 5, 6. These values are shared by space and time. But since you are moving here, then this is your bit, the bit 7, the bit 37. This bit 37, to calculate, you can calculate directly the space-time interval by getting 7 squared minus 3 squared, and that gives you 40. Very simple. That's what you can do. Then you don't need to stop there. You have also to calculate the time interval. So if you are calculating the interval between the interval of these two values, you have to calculate 3 values that are needed. This value of the space, what we call space-time interval, as you see, then you have to calculate also the time interval and space interval. The speed you need in order for you to reach to that point is that you need to calculate that also. You have to know it. I will explain later why we need to know it. Then we do this because the space-time interval is the product of space interval by time interval. So you do that, you have 40. Now you may be wondering, why these values, where they come from? In the mathematics we have been doing so far, we did not understand exactly where these values came from. But here I'm going to show you something very surprising. Something that will surprise you. This is the one. You go from point A to point B, passing through 4, 5, 6. So this is in time, if you see. But you must know that at the same time you are moving through space. Therefore, you are carrying both space and time. Then the values you have between here are shared by space and time. That's why we can open the space between the two values. We can open that. When we open the space here, these values will move to space and also to time, so they will duplicate. Why? Because they belong to space and time at the same time. Then let's sum up all these values. Now, sum up the values. You see, 3 plus 7, those are the one we know already. Then 2 times plus 2 times these values between, the in-between values, which are 4, 5, and 6. That gives us, here we have already 10 plus 2 times 15 equal 10 plus equal 40. You know, the result you get is 40. So you see that the 40 is not just given by random. It came from this process of opening the dimensions between values. It means we are opening the bit of information. When we open the bits of information, we see that we are increasing the dimensions. So we go from one dimension like this, and we move to 2 dimensions. We can go now even for 3 dimensions. We will be doing that also for 3 dimensions. This is the miracle that happened in this. And by opening these dimensions of space-time, then we will be able to truly identify all the values needed in order to identify a bit of information, a bit of space-time. It's very important to know this. This is an exercise you can do. You can do at home. Start doing already, because you will need this in the future. Even if you are not a mathematician, but because this involves the new notion, what we call the relativity of numbers. Because you did not study relativity of numbers in school, so you don't understand these things. You don't know that this exists. By just opening dimensions, I will show you also how to do the 3-dimension opening. We will do that in the future. Then it tells us where the values come from. And more values we will be finding here. We will have a whole pyramid of values, because this is about information. Actually, in the mathematics that we have been studying, if you go from 3 to 7, you just calculate the difference between the two. If you tell you what is the interval, of course, for you, it's only, interval here is 7 minus 3. That's all you know. But there are other values you can calculate also, if you know the relativity of numbers. So now let's move to this point where we have to understand exactly why we are using this sign of little cell here. We calculated already this in the point in the bit of 3 and 4. We got this result 7. What we are interested in is just the results. That's why I don't need to explain what I have said already. The result you see is 7. The 7 here is not a simple 7. Why? Because, as I have told you, we open dimensions. So we go from one dimension to we open, and the line of space-time is a 2-dimensional line. Therefore, when you open, the value you get has the value of a square. So it is a second dimension 7 that you have here, but it is not exactly 7 squared. It's different from 7 squared. It means 7 times one little cell we call squared. So this cell here, this square cell, the square cell serves as the storage of your information in your computer. So now you understand where we are heading to. We are talking about the bits of space-time. bits of space-time allow us to measure exactly how much information you can save between, because in the computers we use numbers, but we don't know the relativity of numbers. That's why we could not understand that we could open space between the numbers and load more information in our computers. So the future generation of computers will be based on this mathematics. This is the point. You don't need to bargain. This is really what will happen. I am just informing you. Why? Because we are going to discover the new structure, how really computers should be built. The true computers. The computers we have today, yes, they do, but they are problematic. So the real computers, which will come soon, will be working based on this mathematics. That's why I'm not here to just demonstrate that I know the mathematics, I understand the mathematics. No, I'm not to that. I am here to convey a message that the future is looking so bright for those who can understand what I am explaining here. So now we understand that if you have your object, a three-dimensional object, you can store the information in the space-time, in the space-time interval, and the size there will be, we saw the other one is 40, for example, from 3 to 7, you have the result there is 40. Therefore, you have to have 40 small cells like this to install. So it will take a lot of information. We can load a lot of information. So let's move on in our last point we are going to discuss about here. The reason why we have to understand the bits of information. You move from a point 3 to point 7. That's what we have seen. You can calculate the space-time interval. You calculate the space-time interval between the 2 points. That's all you think you can do, but it is not so. You have still to mention the time interval and space interval. So these three values, 40, 4, and 10, are very important for us to fully describe the bit of 3, 7. Why? Because they will help us to understand one thing. What is it? As you see here, we go from a point A to a point B. The definition says, the definition of relativity says that we have to calculate the events, then calculate also the space between events. So far in this chapter, we have been calculating only the interval. It means the between events. So all these numbers describe the between event. You have space-time interval, time interval, and space interval. So when you are asked, for example, what is a space between 3 and 7, it is not 7 minus 3. 7 minus 3 is the time interval only. The space interval is 10. The space-time interval is, so now we have a new understanding of numbers, that we can calculate the space interval, the time interval, and the space-time interval. So now that's what we have been doing so far in this chapter. But still, we need to know where these events happen in space and in time. So we have to tell exactly time A, time B, space A, space B. We have to tell that. Therefore, as you see, it is suggesting that these numbers, so the one you call here space, the space between the two events, this is the difference between the two space, the space B minus space A. This is the gap between the two events. So 10. Then the time between the two events is mentioned as a T, B, time B minus time A. You may think that, but we have already, this is we have already that one here. We know that it's located, the event here took place at the point 3 and the other point took place at the point 7. No, you are wrong. In space-time, we have to go in the real world, the three-dimensional. So that's why we need to create a three-dimensional space-time here. We have to create values. So the values that we'll get here will come from the 3 dimensions. So we have to complete that. Where will we get these values from? These values will come exactly when we study first how space and time interact. So we will have almost 3 chapters again before we will give the answer to this question, because there are values here of A and values of event B that we need to reveal where did this event really take place in space, and these took place in space and time. Space and time. So we have to know that. That's why we need these 3 values. But as I have said, we still need to understand first how space and time interact. Therefore, please follow my explanations in the next chapters. Then you will be able to understand where these values will come. Because so far, relativity was not able to do this. This is the first time we are going to open the box. We are going to reveal exactly what should be done. And it is here that lies the secret of everything. Singularity, black holes, the Big Bang. It is through this that you will be able to understand all of that, by opening these dimensions. Therefore, we need to reveal first these values. So please follow me again next time as we are going to study the interaction between space and time. Thank you very much.